On to section 3.8, derivatives of inverse functions and logarithms. Okay, so got a little bit more stuff to do with the implicit differentiation before we get to the applications. The big goal in this section is to differentiate really logarithms, and in the next section we'll differentiate the inverse trig functions. And that'll pretty much be it for differentiation. You'll know all the functions that you'll be differentiating, and you'll know all the techniques of differentiation. All right, so 3.8 is derivatives of inverse functions and logarithms. So the inverse function stuff will, in this section, apply to logarithms, and in the next section, apply to inverse trig functions. So the plan here is to explore the relationship between the derivative of an invertible function and the derivative of its inverse. What you know at this stage is logarithms and exponential functions are inverses of each other. We know how to differentiate exponential functions, and we're going to use that knowledge to figure out how to differentiate logarithmic functions. So let's start with everybody's favorite example of a function and its inverse. Let's start with the squaring function with a restricted domain and its inverse, the square root function. So recall the graph of a one-to-one function f and its inverse are mirror images about the line y equals x, and that's what's going to drive the first result that we state concerning how their derivatives are related, how the derivative of a function and its inverse are related. Something to do with the fact of this type of symmetry and an interchanging of the role of x and y from a function to its inverse. So here in the figure below, we see the graph of, in blue, the one-to-one function, f of x equals x squared, with the added constraint that x is greater than or equal to 0. All that highlighted stuff there is the name of the function. So it's not simply the squaring function, it's the squaring function with a restriction on the domain that we only keep input values that are non-negative. Otherwise, we don't have one-to-oneness. If we keep both positive and negative stuff, you don't have one-to-oneness, you don't have an inverse function. So this particular function, as we saw when we talked about inverse functions in the review material in chapter 1, the inverse of this function is a square root function. Here's the squaring function with a restricted domain drawn in blue, and here's the square root function, its inverse, drawn in yellow. And indeed, if we were to draw the line y equals x, which would pass through the origin and the point 1, 1, for example, which lies on both of these curves. And if we interchange the roles of x and y, if we folded over the graph of, say, the blue function about the line y equals x, it would lie on top of the yellow function, and conversely. The usual mirror image type relationship between the graph of a function and its inverse. Okay, so what we want to do is look at the slope of the function. Just think of the blue one as the function and the yellow one as its inverse. The slope of the function, the blue one, at the point 2,4, and the slope of its inverse at the point 4,2. So, as we often do with inverse functions, we've interchanged the roles of x and y. So we've got the point 2,4 on the function and the point 4,2 on the inverse function. And what you'll find, and easily could show using derivatives, is that the slope of the tangent line to the function at point 2, 4 is 4, and the slope of the inverse function at the point 4, 2 is 1/4. They're reciprocals of each other, not negative reciprocals. We saw some of that recently in the context of orthogonal lines. Here we seem to have a slope in one case that's a reciprocal of the slope in the other case, which makes sense because when we move from a function to its inverse, there's this interchanging of the roles of x and y. Well, now slope is, from high school, slope is rise over run. also from high school and maybe a little bit more from in here, it was a change in y over the change in x. Okay, well, if you interchange the roles of x and y, you're going to swap that division. Instead of having change in y over change in x, you'll have change in x over change in y when you interchange the roles of x and y. So that's the reason we get this kind of reciprocal relationship between these slopes. But it's a long story. We went from a function to its inverse. We looked at a point 2, 4 on this one and a point 4, 2 on that one. And in that situation, we got the slopes to be reciprocals of each other. It's all being driven by this mirror image relationship between a function and its inverse. Here's the rule that tells us how those derivatives are related. Actually, it's a really elementary rule. The statement of it is, I would agree, it's a little clunky. So Theorem 3.3, the derivative rule for inverses says, if f has an interval as its domain and f prime exists and is never 0 on that interval, then the inverse is differentiable at every point in its domain, and the value of the derivative of the inverse, f inverse, little prime there means take the derivative of f inverse. The derivative of the inverse at a point B in the domain of f inverse is the reciprocal of the value of f prime at the point A equals f inverse of B. All right, so it's a little involved. There's this B and f inverse of B stuff going on. It's what happened in that picture on the previous slide, previous page. Symbolically, the relationship is the derivative of the inverse function evaluated at x equals b is the reciprocal of the derivative of the function itself evaluated at f inverse of b, evaluated at what they've called a here. Let's go through proof of it. So we'll make use of this as best we can. Let's look at a proof, and it's one of those cases where actually the proof is quite easy. What do you know? I know the definition of inverse function, which deals with compositions of functions, and I know the chain rule. And that's it turns out that's all we need. Okay. So by definition of an inverse function, f inverse of f of x equals x for all x in the domain of f. We could also inverse the roles of these and say f of f inverse of x equals x as well. Anyhow, the composition of the functions equals the identity function, regardless of the order in which we take the composition. We're going to take it in this order for reasons to become apparent here in the next couple of lines. So what we'll do is take this equation and differentiate both sides. Implicitly, we'll take the chain rule to differentiate. So we'll differentiate the composition, f inverse of f of x. So the f of x is the inner function and the f inverse function is the outer function. And we'll differentiate the right-hand side of this little equation, which is just x. Derivative of x is 1, no problem there. But here we've got a composition. How do you differentiate a composition? Chain rule says, differentiate the outer function, f inverse prime, rewrite the inner function, and then there's a chain rule with a little arrow, multiply by the derivative of the inner function, multiply by f prime of x. Let's see, if we rearrange that, divide both sides by f prime of x, notice there was a comment up here in the hypotheses that f prime of x is never 0. Good thing, because we're about to divide by it. So that's why that's a hypothesis. So we get the derivative of the inverse function evaluated at f of x equals 1 over f prime of x. Effectively, that's what this theorem says. And the proof of it is so easy. You just take this little definition of inverse function and differentiate using the chain rule, and it produces this. This doesn't look exactly like what's written up there, so let's fiddle with it a little bit. Okay, so if we set x equal to f inverse of b, in this equation here, then we'll have f inverse prime of f of x, that is, replace the x with f inverse of b. Now, f of f inverse of b is just b itself. So this would be the derivative of the inverse evaluated at b, which is what this is, the derivative of the inverse evaluated at b. And on the right-hand side, we're again plugging in x equals f inverse of b for x. So we get 1 over f prime of f inverse of b, which is what this says. You get 1 over the derivative of the original function evaluated at f inverse of b. So here's the statement that we're stuck with. The idea behind it, very elementary. Definition of inverse functions in a chain rule. Let's do an example to illustrate it. So this comes next in the notes. It says, let f of x be x squared minus 4x minus 5, where x is greater than 2. Why did they add this x greater than 2 condition? Must be to make a one-to-one function. If we graph y equals x squared minus 4x minus 5, full stop, you graph this thing, that ain't going to be one-to-one, and it won't have an inverse, and we want to have a conversation about inverse functions. So that's the reason this little condition here has been added. The question is, find the value of the derivative of the inverse function at the point x equals 0, which, by the way, is f of 5. Okay, well, we just stated in Theorem 3.3 that this is the relationship between the derivative of an inverse function and the derivative of a function itself. They're evaluated at different places, as given, as we saw. So we just got to make this question fit what we know, and this is what we know. Okay, so let's see. They want the inverse function evaluated at 0. We know how to evaluate the inverse function at b. So we want b to be 0. So we're taking b to be 0. We need f inverse of b. F inverse of b, we just said we want b to be 0. That'd be f inverse of 0. F inverse of 0 is 5 because f of 5 is 0. So apply the inverse function to both sides of this little equation if you like. So f inverse of 0 is 5, and now it's a matter of finding the derivative of the original function, easy enough, and plugging in the right thing in the right place. The funny thing is, we're about to answer their question, what's the value of the derivative of the inverse function at this point, without ever finding the derivative of the inverse function. We actually end up just using the derivative of the function itself. Buried underneath all these symbols here is that geometric relationship between a function and its inverse in terms of the interchanging of x and y and the mirror image of their graphs. So we need the derivative of the original function. So differentiate this function, easy, 2x minus 4. So df dx is 2x minus 4. Now plug the right thing in the right place. So the derivative of the inverse evaluated at b, evaluated at 0, what they wanted, is 1 over the derivative of the function, 2x minus 4, evaluated at f inverse of b. That is f inverse of 0, that is at 5. They told us that. So we plug 5 in for x, we get 2 times 5 minus 4, 1 over, that's 1/6. So it's not very complicated. The calculus was easy enough, and we're just differentiating that quadratic. The rest of it was really bookkeeping and putting the right thing in the right place and realizing that the question they asked is actually something we can answer with the information we know. So back to the notes, that took care of the example of that. We're going to look at exponential functions and use them to differentiate log functions. We can differentiate e to the x, and the natural log of x is the inverse function of e to the x. So we can use that theorem above to differentiate the natural log of x. So if we can differentiate a function, we can use theorem 3.3 to differentiate its inverse. And really, we can mostly establish this just from the chain rule and the meaning of inverse function. Okay, so claim is in theorem 3.8.a, this is a big deal. You're learning how to differentiate a new function. I told you in the past, we're going to differentiate a new function, you'll have to go back to the definition of derivative. I guess I was wrong. Here we've got this theorem 3.3 that lets us use the fact that we know how to differentiate the inverse function. So we're using that. We don't have to go all the way back to the definition. We differentiated the exponential function using the definition. This one, theorem 3.3, will let us weasel around the application of the definition of derivative and all that stuff about the limit as h approaches 0. And establishing this, actually establishing this and its generalization will take us just a few lines. Claim is, for x greater than 0, the derivative with respect to x of the natural log of x equals 1 over x. So the derivative of log x, natural log of x, is 1 over x. Why is there the constraint that x is greater than 0? Because that's the domain of the natural log function. You can't take logs of 0, nobody can. You can't take the logs of negatives because I won't let you. It involves complex numbers. So for us, we need x to be greater than 0 for this to be meaningful. So really no constraint by saying x is greater than 0. And the claim is derivative of the log function is 1 over x. If we looked at a composition, if u, say, equals u of x, I think the book leaves the of x stuff off, I'm a little more comfortable, and I suspect you are too, if I explicitly write out that u is a function of x. If u, or u of x, is a differentiable function of x, then for all x such that u of x is greater than 0, we're going to put that in the log function in a second, we have the derivative with respect to x of the log of u, or if you like, the derivative with respect to x of the log of u of x is 1 over u du dx, or 1 over u of x, u prime of x. That's the claim. How are we going to justify it? Looks like we're going to be using a chain rule because of the little arrows there. And we are going to be using the chain rule. Here it is. Okay. There's the claim. First, let's establish this part. All right. F of x equals e to the x is differentiable. So the theorem says we can differentiate log x. That is, we can differentiate the inverse of e to the x, right? F of x equals e to the x. We can differentiate the inverse of e to the x. We can differentiate log x as given here. It's 1 over f prime of f inverse of x. So we can effectively relate, and this is what we had in the proof of that theorem 3.3. We have the derivative of the inverse by simply having, with appropriate manipulations, the derivative of the original function. But you evaluate it some exotic place at f inverse of x. But we're taking f of x to be e to the x, so the inverse function is log x. What we get from the theorem is this equation right here. F prime, that'd be the derivative of e to the x. What's the derivative of e to the x? E to the x. So we'll simply have the exponential function evaluated here. So that's e to the f inverse of x. That's read f inverse of x. That's not f minus 1. I mean, the fonts are close in size, but that really is an f inverse of x. We got there f inverse of x was log x. So we replace the f inverse of x with log x. We got e to the log x. Hey, an exponential function and its inverse, those compose to give the identity function. I've said in the past, it's like they cancel out. It's not really algebraic cancellation. It's composition of inverse functions. But anyhow, they're gone and we're left with the x. And that's the first part. I thought we'd get the whole thing on one slide. We have to go to the second slide, but that establishes the first part. The derivative of log x equals 1 over x. The second part will just follow from the chain rule. That's why there's those little arrows there. So derivative of the natural log of something is 1 over this something. unless the something is complicated, like a u of x, and then I have to use a chain rule. So when we differentiate the natural log of u of x, chain rule says we'll differentiate with respect to u, natural log of u, and then multiply by the derivative of u with respect to x. Chain rule, remember this? It looks like the du's cancel. They don't because it's not multiplication. And well, it is multiplication, not division, though. The little bars don't represent division. They represent derivatives. They're not quotients. They're limits of quotients. But this is what the chain rule said. And in the back of your head, some idea of cancellation of du's is a good way to remember what the chain rule says. It won't do because this is not cancellation. It's a chain rule. So we differentiate the log function that says take 1 over whatever's inside, and then we multiply by the derivative of the stuff inside. So we multiply by du dx, and that's exactly what was claimed. Here it is in terms of the x's and the primes. So you can differentiate a log function. You can differentiate a log function composed with something else. You can differentiate something else composed with a log function, as long as you know how to differentiate the something else. Be the chain rule. So something that's in the book as an example, we'll do several exercises. I didn't include the example in the notes here, is if we'll consider the function natural log of the absolute value of x. Now I don't have to assume x is positive. I still have to assume it's non-zero because we can't take the log of 0. But we can take the log of anything positive, and the absolute value of x is going to be positive as long as x isn't 0. And the claim is the derivative with respect to x of this function, natural log of the absolute value of x, is 1 over x. Straightforward to establish. We've already established it for x positive upstairs. We do a similar type thing. We could use this chain rule stuff to establish it when x is negative even. All right, let's do 3 examples. And this little factoid that the derivative of the log of the absolute value of x is also 1 over x. This will come up at some point in the near future, possibly in these exercises. But let's look at 3 more exercises where we're simply going to differentiate things that have logs in them now. Derivative of y equals log of sine x. How do you do that? Differentiate the log function first. We got a composition of functions. So we'll have 1 over whatever's inside. Sine x is inside. And then we'll multiply by the derivative of sine, which is cosine. So derivative of log, 1 over. Tack on the derivative of the stuff inside. That's explicitly what Theorem 3.8.a said. You're probably better off remembering I differentiate logs by taking reciprocals, and then I respect the chain rule. The chain rule then says tack on the derivative of the inner stuff. So that's where the cosine comes from. If you want to simplify, we get cosine over sine, which is cotangent. So easy enough to take derivatives involving log functions. Just know the technique that the derivative of log is 1 over. All right, then what's the derivative of log of log of log of x? Well, I expect to see some 1 over stuff in it. We got a composition. We got a composition of 3 levels of functions. You've got a log function, level 1, inside another log function, level 2, inside yet another log function, level 3. So we've got not a composition of 1 function inside another, not a composition of 2 functions, but a composition of 3 functions. 3 functions, we'll use a chain rule twice. Okay. Derivative of the log function is a 1 over. We'll differentiate from outside in. So first differentiate this log function. When you differentiate the first log function, that'll give you 1 over whatever's inside that first log function. What's inside that first log function is these second 2 log functions. So we get 1 over natural log of x. This first log function has been differentiated away. See, we got 1 over the stuff inside. 1 over u of x, if you like the notation given in that previous theorem. And in the chain rule says, now you got to multiply by the derivative of the natural log of x. Okay, we'll work from the outside in again. You'll differentiate this log function, the outer of the 2, which means take a reciprocal of 1 over the stuff inside that log function. The stuff inside that log function is another log of x. And then multiply, chain rule says, by the derivative of that log of x, which is 1 over x. Told you so. We're going to use the chain rule twice. Yeah, we used it twice, and I can see where we used it with the little arrows indicating applications of the chain rule. I predicted twice because we had 3 levels of functions. Each time we had a reciprocal of the stuff inside. Reciprocal of the stuff inside, reciprocal of the stuff inside, reciprocal of the stuff inside. And there are 3 of those reciprocals because there's 3 log functions that were differentiated. And well, fine, that's the derivative. I can move it around the pieces a little bit, maybe write it like this. This goes from x to log of x. The more complicated stuff is written on the right, just kind of an informal, common way to present math material. But whatever, this is the derivative. Once you got it all in square brackets, you've got the derivative, unless you want to simplify it. I'm happy with this, unless I got to do something with the derivative. Another example, find dy d theta when y equals, this is quite a composition here, the natural log of the square root of sine theta times cosine theta divided by 1 plus 2 natural log of theta. Okay, so as is, we've got inside a log function this thing here. It's a quotient. So I'm seeing, unless I'm clever, I see a quotient rule. In that quotient, there's a composition. The square root of sine theta cosine theta. So that'd be composition, that'd be chain rule. And then inside that, there's a product. And that product would be a product rule. So I'm seeing product rules, chain rules, quotient rules. And all that's just happening from taking the derivative of what's inside the log function. We could do all of that. But let's use properties of logarithms first. You got the log of a quotient. Well, let's take advantage of the power of the log function when it meets a quotient. It says the log of the quotient is the difference of the logs. So let's take the log of this divided by that and write it as the log of this minus the log of that. They're equal. It's a property of logarithms. And the quotient's gone, and now I don't have to deal with a quotient rule. Well, can you do some more of that? I believe you can. Let's take this square root thing and write it as a 1/2 exponent. Same thing, it's what the square root means. Hey, another property of logs says you can take exponents outside the log function as coefficients. So we can bring that 1/2 out front as a coefficient. What was I talking about with the square to this stuff here? It was a chain rule. We just lost a chain rule using properties of logarithms. We still got a product here, but wait, that's not all. Hey, the log of the product is the sum of the logarithms, another property of logarithms. So we could write the log of sine theta times cosine theta as the log of sine theta plus the log of cosine theta. So let's do that too. There's a 1/2 out front. We've done the distribution when we wrote it as a sum. Anything else, log of 1 plus 2 log theta, you know anything about the log of the sum? No. You know things about logs of products like this and logs of quotients like that, but you don't know anything about the log of a sum. The log of a sum you're stuck with. In other words, we got all the mileage we're going to get out of properties of logarithms down to here. But this ain't hard to differentiate. It's just a log of some stuff. And we had a theorem that told us exactly what to do with that. Differentiate, okay, we got the 1/2 out front. Differentiate log sine theta, 1 over sine theta times cosine theta times the derivative of the stuff inside. So 1 over the stuff inside times the derivative of the stuff inside. We actually did this in a couple examples ago. Similarly, derivative of log cosine theta, 1 over the cosine theta times the derivative of the stuff inside. The derivative of cosine theta is negative sine theta. And a similar thing here. Natural log of 1 plus 2 theta, derivative is 1 over the 1 plus 2 theta times the derivative of 1 plus 2 theta. Derivative of 1 is 0, just to see where everything came from. Plus 2, derivative of natural log of theta is 1 over theta. differentiating with respect to theta. All right, and let's see, we had differentiated. Got a little typo here. We had differentiated at this stage. I don't have equality here. This is actually the derivative. So the derivative, I should stick a dy d theta right here. Dy d theta equals this quantity here where we've differentiated. I will fix that typo in the notes. And we can clean it up a little bit if you're so possessed. Cosine over sine is cotangent. Sine over cosine is tangent. There's negative out front. And we can condense this a little bit and write it in this form if you like. But yeah, my bad. This is the derivative. This should read dy d theta equals right here. And there's what we get for the derivative. Now, the punchline on that one was, geez, it was awfully convenient having that logarithm out front and taking advantage of the properties of logarithms before differentiating. I was worried about a quotient. No need. I can write the log of a quotient as a difference of logs, and the quotient rule's gone. I was worried about a chain rule. Well, for this kind of chain rule, I can write that square root as an exponent of a half and bring it out front, and that piece of the chain rule's gone. I got a product. Well, I can write the log of a product as a sum of the logs, and that product rule is gone. Quotient rule's gone. Product rule's gone. The chain rule that was caused by the square root function is gone. Now, there's still some compositions here. Natural log of sine theta, that'll require a chain rule. There you go. Natural log cosine theta, that'll require a chain rule. Actually, even this one will require a chain rule. I see we use a chain rule 3 times in finding dy d theta. But that's easier than taking the reciprocal of what's inside and multiplying by the derivative of what's inside. So much so, we did those 3 examples, that I'm going to say the previous examples suggest that the computation of certain derivatives, those that got lots of products, quotients, and raising to powers in them, those could be simplified if we first took a natural logarithm. Now that changes the function, but if we're careful, it could certainly be to our advantage to take a logarithm and then differentiate, but it changes the function. We'll have to keep an eye on that. This technique is called logarithmic differentiation, and it's really just based on the chain rule. So, how about this one? This is exercise 52 from the section. It says, consider y equals the square root of x plus 1 to the 10th power divided by 2x plus 1 to the 5th power. Find y prime by first taking a natural logarithm and being very, very careful. This will require some implicit differentiation. First off, as stated, we got the square root of something. Okay, that'll be a composition. That'll be chain rule. We got a quotient, because there's quotient there, that'll be quotient rule. In the numerator, we've raised to a power. That'll be another chain rule. In the denominator, we've raised to a power. That'll be another chain rule. Unless we take advantage of the properties of logarithms. So let's look at what we get by taking a log. Okay, we had y equals this stuff here. So let's take a log of both sides. And we get the log of y equals the log of this stuff here. So we no longer have y, we have the log of y, but that's okay, we'll deal with it. And the reason we wanted to do this was we can take that square root and write it as a power of a half. We've got this stuff inside a log function, that exponent of 2 come out front as a coefficient. And the big square root chain rule thing we had, it's gone. Now we've got a log of a quotient. Well, the log of a quotient is the difference of the logs. So we can write this as the log of the numerator minus the log of the denominator. There's a 1/2 out front to take care of that. 1/2, parentheses, log of the numerator minus log of the denominator, other parentheses. Hey, these are exponents inside a log function. Just like with a 1/2, they can come out front as coefficients. So we get the 10 out front here, the 5 out front here. The chain rule we would have had to use based on the fact that we've got something to the 10th power. And the chain rule we would have had to use based on the fact that we have something to the 5th power, gone. We get that 1/2. Let's go ahead and distribute that, producing 5 natural log x plus 1 minus 5/2 natural log 2x plus 1. And that's it's a natural log of y. It's not y itself. Well, it's an equation that relates y and x. Let's differentiate it. So we'll differentiate both sides implicitly, that was actually the instructions, with respect to x. Differentiate with respect to x, natural log of y. That's a composition of functions. That's a chain rule that we introduced. So we got rid of lots of chain rules along the way, but we've introduced a new one. And then differentiate with respect to x, the right-hand side. Right-hand side's easy. Turns out the left-hand side's not very hard either. So here's where we left off. So we've introduced a log function and taken advantage of properties of logarithms. So we want to differentiate both sides. Right-hand side, let's do that first because that's what it's typeset. Differentiate 5 times natural log x plus 1. That'll be 5 times 1 over x plus 1. Here it is, 1 over x plus 1 times the derivative of x plus 1. So say if the chain rule is just 1. Minus 5/2, differentiating. Differentiating this will be 1 over the 2x plus 1 times the derivative of 2x plus 1, which is 2. You want to clean this up? Yeah, probably. We haven't dealt with the left-hand side yet. The 2's cancel, and that's about it. I can put the 5 in the numerator, I guess. And we're left with something like this. So here's the derivative with respect to x of the natural log of y. We took care of differentiating the x part. Now we need to take care of differentiating the left-hand side, the natural log of y part. Well, that's a composition of functions of x. Natural log function, and inside it is the y function. Y is a function of x. Can you tell me what y is explicitly in terms of x? Yeah, we were given it, in fact. But it was going to be hard to differentiate this. We've swapped a whole bunch of chain rules and a quotient rule, potentially a product rule, but not in this one. We've swapped all that stuff for this little bitty bit of chain rule stuff here, where we take 1 over y and multiply by dy dx. And dy dx is the thing we're looking for. Y prime is what we're looking for. So we've got 1 over y, dy dx equals this other side of the equation we just saw equals this. Let's carry that to the next slide. And you want dy dx, cross multiply by y. Get the y out of the way. Bring the y to the other side. You'll have dy dx equals y times this remaining stuff. Do you know what y is? I do. They gave it to us. Well, then write it down. And we've got dy dx in terms of x, like you wanted. We pull this trick of taking a natural log, of differentiating, of applying the technique of logarithmic differentiation. And this was computationally easier than it would have been just plowing into this as is. I mean, you would have got the same thing. It wouldn't have been quite as easy. We lost a lot of complicated rules of differentiation, and we introduced this extra little step here, but that ain't a hard step. It's well worth the price of the ticket to swap all them quotient rule, chain rule things for this little bitty chain rule deal here. You cross multiply, you know what y is, you substitute in, there's a derivative. Back to the notes. Okay, so shifting gears a little bit, I've been complaining about this irrational exponent stuff for the longest time. We're finally in a position where we can deal with that. When a is a real number, then by a to the n, where n is a positive integer, we mean a times a times a, n times. When negative n is a negative integer, a to the negative m means 1 over a to the m power, or 1 over a times 1 over a times 1 over a, m times. If negative m is a negative integer, m itself is positive. So it makes sense to talk about a number of times, m times. So the negative means reciprocal. Positive integers mean repeated multiplication. How about fractions? Rational numbers. If m over n is a rational number, where m and n are both integers, n's not 0 because you ain't dividing by 0 now or ever, then what you mean by a to the m over n is the nth root of a to the m. So the m means repeated multiplication, and the n, the denominator part, means take a root. Okay, that could be a problem because we can't take square roots of negatives or fourth roots of negatives or sixth roots of negatives. So there's a constraint comes in here. You have to avoid the square roots of negatives effectively because I won't let you take square roots of negatives. Come back and see me in complex variables, a senior level class, and we'll take care of it in there. And we will take square roots of negatives. There's a lot of other details that'll come with that as well, it turns out. But algebraically, we're not taking square roots of negatives in here, so I worry about that. So the punchline here is, do you know what a to the r power means? Yeah, if r is an integer, positive integer, it means repeated multiplication. Negative integer, it means repeated multiplication of the reciprocal of a. For a rational number, it means repeated multiplication and then the extraction of a root, you know, if you don't have the square root of negative stuff. So that takes care of integers and rational numbers. Of course, integers are examples of rational numbers. What about irrational numbers? What if the exponent is irrational? And we mentioned this, I think in the chapter 1 material. I think it was in the preliminary stuff. Well, we're about to use the natural exponential function to define what it means to raise a positive real number to any real number power, including rational numbers. So for a greater than 0, all right, that being said, we're avoiding any square roots of negatives because we're not having negative numbers in the conversation in this definition. And we never will for irrational powers. For rational powers, maybe we can, maybe we can't deal with a to a rational power. I can't if that rational number is 1/2 because I can't take square roots of negatives. So basically the conversation has sort of been set aside for negative numbers. So for a greater than 0, the very definition of a to the x, where x is any real number, is e to the x natural log of a. And you think of it like this. Well, here we've got an exponential function, and here we've got its inverse. So in some sense, e to the natural log of a, composition of inverse functions, it's kind of like the e and the natural log of a cancel, leaving us with an a in the base, leaving us with this. And we're taking it as a definition, which is fine. The exponential function has as its domain all real numbers, so we're good to go. And this right-hand side actually makes sense. And we can take the logarithm of a, provided a is positive, non-negative, and non-zero. So if a is positive, then the natural log thing is defined. So this is defined for all real numbers. Any real number x, this makes sense. In the highlighted part, that's what we're defining as a to the x. Motivation being thinking about the log function and the exponential function is canceling. Okay, so we want to differentiate this new function a to the x. Because that's what you do in Calculus 1, that's why. Actually, if we're doing differentiation, we ought to be talking about natural exponentials and natural logs. Here's why. So if a is greater than 0, then u is a differentiable function of x, then a to the u is a differentiable function of x, and the derivative with respect to x of a to the u is the natural log of a times a to the u times du dx. Where'd that highlighted natural log of a come from? Must have come out of our definition of a to the x power. Let's go through a proof of that. Next, let's establish that. This we can do in a single slide. First, let's show the derivative with respect to x of a to the x is apparently this. And then we'll use a chain rule to get this extra little piece. All right, what do you mean by a to the x? We defined it as e to the x natural log of a. All right, here we have a composition of functions. The exponential function is the outer function. The inner function is x times natural log of a. So we'll need the chain rule to differentiate. Differentiate the exponential function. Nothing happens. You just rewrite it. Derivative of an exponential function is itself, base e. Rewrite the inner function. And the chain rule says now you got to multiply by the derivative of the inner function, the derivative of x natural log of a with respect to x. That's just a constant multiple of x, so the derivative is that constant multiple. It's that natural log of a. That's where the natural log of a came from. It came out of that exponent, ultimately, when we differentiated. So we see the derivative of a to the x is natural log of a times a to the x. What if a equaled e? Then we'd have the natural log of e, that's 1, times e to the x. We'd have the derivative of e to the x is e to the x. How clean is that? When the base of the exponential function isn't e, you get this extra ugly little factor. You get this natural log of a factor to pop up. That's what's natural about the natural exponential function, in fact. So there's how you differentiate a to the x. What if you have in the exponent a function of x itself, and you have a to the u, and you differentiate with respect to x? Well, you differentiate the a to the u with respect to u, and you know how to do that. You get natural log of a to the u out front, and then the chain rule sticks a du dx on it, as was claimed up here. So there's how you differentiate when you have exponential functions to a base other than e, though I would say if you're doing calculus, use natural exponentials. Use exponentials base e. And you don't have to keep up with all these ugly constants. The previous theorem implies, among other things, we actually did this computation, the derivative of a to the x is a to the x times this icky constant natural log of a. If we took a to be e, as I commented, well, a natural log of e is 1, we'd get the derivative of e to the x is e to the x. I mentioned this before, but that's what's natural about the natural exponential function. It's the only exponential function that when you differentiate it, you get the function back. All the others, you get some oddball multiple of the exponential function back when you differentiate. Well, you get a multiple here as well, just that multiple is 1 when you deal with natural exponential functions. So that's what's natural about a natural exponential function. I've mentioned before, maybe in chapter 1, and also when we probably encountered derivatives of exponential functions. What's natural about natural exponentials and natural logs is a calculus thing. It's a differentiation property that they have. That's why in pre-calculus or in high school, if somebody told you, we're calling this a natural exponential function, where this number e is some weird irrational number, 2.718 something or other, they couldn't really tell you what was natural about it because you didn't know what differentiation was. Now you know. What's natural about the natural exponential function, say, is the clean way that's differentiated. A property shared by no other exponential functions. They all, when differentiated, yield some awkward multiple of the original exponential function. So that's what's natural about the natural log function. I guess it was in section 3.3 we talked about differentiating exponential functions. We had gone through and shown from the definition of derivative of an exponential function that the derivative with respect to x of a to the x was a to the x times this weird limit thing. And we played around with it in terms of some pictures, and we made some claims that we didn't justify very well. Well, that thing there turns out to be the natural log of a. As we just saw, if you differentiate a to the x, what you get out is a to the x times the natural log of a. And this weird limit thing that we got out of the definition of derivative back in section 3.3, turns out that's the natural log of a. they had used the symbols in this textbook of L sub A in section 3.3 when we encountered that. Yeah, that's because it's the natural logarithm of A. So that motivates their little symbols. But anywho, this weird little limit, turns out this must equal the natural log of A, now that we see how to differentiate. We could maybe plug in A equals E, and we know the natural log of E is 1, to get a funny little limit. The limit as h approaches 0 of e to the h minus 1 over h equals 1. Because I know that limit's going to be the natural log of A. So if A is E, natural log of E is 1. There's a funny little limit property. You won't be evaluating this limit by factor cancel substitute. We've got it some weird indirect way based on the definition of the derivative of an exponential function. Natural exponential function at that. So let's illustrate the fact that we now know how to differentiate exponentials to a base other than e. Let's illustrate it with an example. I find this mildly torturous. If you're taking derivatives, don't use anything but base e for your exponential functions. That's why. And the same holds for log functions. That's why if you take a physics class or an engineering class, a dynamics class, maybe in engineering, dynamics meaning things are moving and those rates of change are described in terms of derivatives. In physics, you deal with dynamics problems as well, where things are moving and dealt with in terms of derivatives. In the physics and engineering classes, you run across logarithms and exponentials, they'll be base e because you're going to do calculus there. You take a physical chemistry class and you talk about rate equations, how fast certain chemical reactions occur. You'll deal with exponentials and logs base e in there as well. You do just a regular old intro chemistry class, maybe where you deal with pH. pH is a log scale. I think it's expressed log base 10. They use common logarithms there. Yeah, but they're not taking derivatives there. You talk decibel scales for loudness. You might mention that in a psychology class. And they'll use a log base 10 scale for that. They'll use common logs for that. Yeah, but they're not taking derivatives there. So if you're in a class where you're taking derivatives, you ought to be using natural exponentials and natural logs. All right, that being said, let's differentiate this exponential function base 2. Ugh. Okay. Y equals 2 to the x squared power. Find the derivative. All right, well, we got the equipment in theorem 3.8.b to differentiate 2 to the x squared power. We'll differentiate the exponential base 2. That means rewrite it, but add on this oddball little factor of natural log of 2. So we've differentiated the outer function, the 2 to the power. It produces this natural log 2 and the 2 to the whatever's the inner. Rewrite the inner's x squared. And then multiply by the derivative of the inner. So it's a chain rule. Chain rule, because it's a composition of functions. Derivative of x squared is 2x, and we can rewrite that in this form here. So that ain't that complicated to differentiate exponentials to other bases. They behave just like regular old e to the functions, regular old natural exponential functions, except you get these natural logs of the base floating around when you deal with derivatives of exponentials to a base other than e. Same thing, similar thing happens with logs to other bases, as we're about to see. Okay, let a be positive, not 1. Define log base a of x to be the natural log of x divided by the natural log of a. This is sometimes called the change of base formula. It's mentioned back in chapter 1 in some of the review material for reasons to be made apparent in calculus 2. You ask a calculator to calculate a logarithm. I don't care what base you want. Usually has a natural log key and it has a common log key, a base 10 log key. It does all its computations using natural logs for reasons that will be made apparent when you study something called power series in calculus 2. But the computations are done using natural logs. You want a log base 10? Well, it computes a natural log and then it converts it to base 10 using this change of base formula. It changes natural logs into different kinds of logs. Logs base A using this 1 over natural log of a multiple. So there's the definition of log base a, just as we defined a to the x above in terms of natural exponentials. Here's a definition of a log base a in terms of natural logarithms. It's a new function. We won't differentiate it. Don't have to go all the way back to the definition of limit because this is so intimately related to the natural log function, and we know how to differentiate it. Actually, we just got a scalar multiple to the natural log function. And the claim is if you differentiate log base a of u of x with respect to x, so it's a composition of functions, it's a log base a with a u of x function, the book's usual notation. I didn't drag it out quite as much in this one, because we've done so much of this. Then we get, the claim is 1 over the natural log of a, 1 over u, du dx. The du dx is going to go there because of the chain rule, of course. And when you differentiate a natural log, you got a 1 over. Yeah, you get a 1 over like with natural logs, but you get this extra funky little factor. You get this 1 over natural log of a thing. Just like when you differentiated exponentials base a, you picked up a natural log of a factor. Here you're picking up a 1 over natural log of a factor when you differentiate log base a. So in both cases, for exponential functions and log functions, base a, they behaved when differentiated a lot like natural exponentials and natural logs, but there was a factor of natural log of a floating around. Here it's in the denominator. For the exponential functions, it was in the numerator. If you used base e, you wouldn't have to worry about any of this because it'd all be 1. But there's the claim. Let's establish that and do a couple of examples of that. Because we have a little bit more stuff to do after that as well. So let's go through a proof of this. It's actually not at all complicated because we know log base a in terms of natural logs. Differentiate with respect to x, log base a of x, first off, then we'll combine it with a chain rule. Well, what is log base a of x? Our definition is it's natural log of x over natural log of a. Natural log of a, well, that's a constant. X is a variable, so take it out. Bring the constant outside of the differentiation, differentiate the log function. Derivative of log x is 1 over x. There you go. So there's a derivative of log base a of x. It's 1 over the natural log of a times 1 over x. Where'd that 1 over natural log of a come from? The way we defined log base a of x as this quantity here. So let's see, that's what we've got out front. Now we'll just combine it with a chain rule. Log base a of u would be the derivative with respect to u of log base a of u times chain rule du dx. We're left with a du dx over there. When we differentiate that log base a of u with respect to u, we get this kind of thing, 1 over u instead. So we get a 1 over log a, 1 over u. Chain rule sticks the du dx on the side. But if you're taking derivatives, what are you doing dealing with logarithms base a? If you're doing rates of change and derivatives, you ought to be using natural logs. But we know how to differentiate logs to other bases. So suppose y is log base 3 of 1 plus theta, natural log of 3. These guys want to know dy d theta. All right, there'll be a 1 over natural log of 3 floating around, you know, from what we just saw. Okay, so we'll take a to be 3, the base of the log. We've got a composition of functions here. The inner function is the 1 plus theta times natural log of 3. So when you differentiate, we'll have a 1 over natural log of 3 that comes out of the fact that they stubbornly wouldn't use log base e. They've used log base 3. Okay, it comes at this cost. And then, as differentiating any logarithm, we'd have 1 over the stuff inside, 1 over 1 plus theta, natural log of 3, times a derivative of 1 plus theta, natural log of 3. Derivative of 1 is 0. Derivative with respect to theta. The theta natural log 3 is that constant, natural log 3. And there's the derivative. There's square brackets. There's little arrows. Where did the 1 over log 3 come from? Is that chain rule stuff? No, no. That's because you were using a log base 3. You get these ugly factors floating around unless you do your logarithms base e. And arguably they're still there. They're just 1 and you can't see them when the base is e. And this can be cleaned up a little bit. Actually, the log 3 there cancels with the log 3 there, and those particular log 3s are gone. But there's a derivative. Don't be using log base 3 if you're going to be taking derivatives. You work in some problem where you ain't taking derivatives and there's something neat about powers of 3, you go right ahead and use log base 3 all you want to. But if you're taking derivatives, you ought to be using natural logs and natural exponentials. Another one, kind of driving home an idea again of how logarithms can be convenient things. Find dy dx when y equals log base 5 of the square root of this stuff here. No, we got a square root inside of a log function. We got properties of logarithms. The properties of logarithms stated back sometime in chapter 1, they're good for log base 5, not just for log base e. If we've proved them, or soon we'll prove them, we'll probably just prove them for logs base e, natural logs, but they hold for the other bases of logarithms as well, as stated in somewhere in chapter 1. So let's split this up. Otherwise, I see some chain rules inside chain rules and a quotient rule. We can break this up and make that a lot easier. So log base 5 of the square root of this stuff. How about first we take the square root radical and write it as a 1/2 exponent. So we'll have natural log of 5 times a half, just natural log of 5 over 2. So that gets rid of the radical, the square root stuff. It's still there. It's still in the over 2 stuff in the exponent. So we haven't changed anything. Hey, we've got an exponent inside a log function, and bring it out front as a coefficient, property of logarithms. Power rule, I think that one was called. We just got rid of the chain rule involving the square root function and chain rule stuff involving this exponent of natural log 5. So we just got rid of both of those. We're still left with a quotient. Well, I ain't done. The log base 5 of a quotient is the log base 5 of the numerator minus log base 5 of denominator. So we'll take the difference of log of the numerator minus log of the denominator. Still got that coefficient out front. Can you do anything else? Yeah, we've got 7 times x there. I don't think I wrote it up like this, but we could split that up as a sum of logarithms if you wanted to. I didn't, but that's the only other thing we could do. There's nothing beyond that that can be done. So let's go through and differentiate. So derivative of y with respect to x is a derivative with respect to x of this stuff here. Let's bring that natural log 5 over 2 thing out front and then take the derivative of the difference, which is the difference of the derivatives, properties of derivatives. Picking up where we left off. So here's that last line from the previous slide. Differentiate log base 5 of 7x. That'd be 1 over the natural log of 5, 1 over the stuff inside, chain rule, derivative of the stuff inside. Differentiate log base 5 of 3x plus 2. That'd be 1 over the natural log of 5, because it's not a natural log. So we get this natural log of 5 thing floating around. Differentiating a log function 1 over 3x plus 2 times the derivative of the stuff inside. The derivative of 3x plus 2 is 3. There's the derivative. Let's clean it up a little bit because it cleans up. I can cancel the log 5 here with both of those. Notice you're subtracting. I can cancel the 7 with this. Anything else? Looks like that's about it. Leaves us with a 1/2 out front. All that's left from this is the 1 over x, and we're left with the 3 in the numerator and the 3x plus 2 in the denominator. So there's what we get for that derivative. Okay, we want to do this one now. Let me check the notes again. Yeah, let's do number 90 now. says use logarithmic differentiation to find dy dx when y equals x to the x plus 1 power. All right. There's some stuff you know and some stuff you don't know. As far as differentiation goes, you know pretty much as much about differentiation as anybody. And nobody knows this as is, but everybody knows the tricks. X to the x plus 1 power. So we've got variables in the base and in variables in the exponent. So I can't treat this like a number to a function of x power. I can't treat it like an exponential function. Also, I can't treat it as a power of x. We don't have x to some specific power. We got x's in the base. We got x's in the exponent. I don't know what to do with that. That we haven't covered. It's not an exponential function. It's not a power of x. It's something new. We don't know how to do it as is. But they gave us the hint to use logarithmic differentiation. They gave you that hint because you can't do anything else. All right, so we'll let y equal x to the x plus 1 power and take a logarithm. Then the log of y is the log of x to the x plus 1 power. Does that gain anything? It does. We've got an exponent inside a log function, comes out front as a coefficient, and we get x plus 1 times log x. We get a product. Can you differentiate that? Absolutely. Product rule, piece of cake. But you took the y and you put it inside a log function. No biggie. I got the chain rule. I can differentiate that too. So we'll differentiate both sides of the equation. We'll differentiate log y, and differentiate this right-hand side, x plus 1 times log x. Product, we'll need the product rule. Derivative of log x, natural log, thankfully. That'd be 1 over the inner function, 1 over y, times the derivative of that inner function, dy dx. Composition of functions. Yeah, it's the log function and the y function. Do you know what y is explicitly in terms of x? Actually, we were given that. So what's dy dx if you know what y is in terms of x? I don't know. That was the whole question. I don't know how to differentiate that. That's why we had to use this little trick. So symbolically, this introduces a dy dx, and that's the thing we're looking for. So we're on the right track. So differentiate implicitly. Natural log of y, 1 over y, dy dx, chain rule, composition, outer function's a log function, inner function, I know what it is, but I don't know what its derivative is. That's the question. Right-hand side, we got a product. So smooth sailing on the right-hand side. We'll have derivative of the first, derivative of x plus 1 with respect to x is 1. There it is in square brackets. Times the second, natural log of x, plus the first, x plus 1, times the derivative of natural log of x is 1 over x. Square brackets, round brackets, plus round brackets, square brackets. Usual thing for a product rule. And we can cross multiply by y. Then we get dy dx equals y times the right-hand side. That's just natural log of x. Could write this as a single quotient, x plus 1 over x. And you know what y is. So now you know what dy dx is. Y was given as x to the x plus 1 power, x to the x plus 1 power. And there's dy dx when y equals x to the x plus 1 power. It's kind of like a little magic trick because we found the derivative of this function and we never really even differentiated that function. So that's pretty messed up. Yeah, the chain rule gave us a formula involving the derivative, which we could solve. But we didn't actually directly compute the derivative of this. We created a formula involving the derivative and solved that. So it's kind of a subtle way that we found the derivative of that function without actually differentiating that function. We differentiated some other stuff. But that's another place where logarithmic differentiation is useful. When you had a function, if you took a log of it and it got rid of chain rules and quotients and product rules, it was useful. Here, you didn't have any choice. It was more than useful. It was necessary that you take a logarithm first because you have no clue how to differentiate that without taking a log. Nobody does. It can't be differentiated without taking a log. So log differentiation is useful sometimes and absolutely necessary other times. It would be when you have variables both in the base and the exponent that you would have to do logarithmic differentiation. All right, let's see how much is left here. General power rule and several more examples. Okay. Next, let's see, where did we get to? We got through that x to the x plus 1 thing. Definition. For x greater than 0, any real number n, define x to the n as e to the n natural log x. Well, this is the same kind of thing we had upstairs when we defined a to the x as e to the x natural log of a. If you'll play around with an appropriate substitution, I won't bore you with the details because we've been at this so long. Make the appropriate substitution. You can rewrite this as that. You move the x's around and the a's around, and you'll produce something of this form. So x to the n, e to the n natural log of x. This is consistent with what we had before. So now I know what it means to take any positive variable x and raise it to n, a real number, any real number exponent. Now we had stated, and that was a big step, what it means to raise a real number, positive real number, to any power. We had stated the general power rule for derivatives before. If you consider x to the n, where n is any real number, the derivative of x to the n is n x to the n minus 1. We have proved this for n an integer and n a rational number. We haven't proved this for n an irrational number, but we're about to, and we're going to use that exponential thing that we just stated and the chain rule. So we had stated this in section 3.3. It was theorem 3.3 part C. We didn't prove it. I think we may have even used it along the way. Well, we got the equipment to prove it now, so we're going to prove this. Claim is derivative of x to the n is n x to the n minus 1, where n is any real number, and positive. If n is negative, then this holds basically if nothing goes wrong. If the derivative exists, x to the n exists, and x to the n minus 1. All three of these exist. The real concern is square roots and negatives, ultimately, with this, even though you're dealing with irrational exponents. But let's go through proof, because based on a chain rule. All right, for x greater than 0, x to the n means, as we just defined it, e to the n natural log of x. So there's the variable. We got a composition of functions. Compositions of functions are differentiated using the chain rule. So we'll differentiate the outer function, the exponential function. Okay, nothing happens. You just rewrite it. Rewrite the inner function, n log x, and multiply by the derivative of the inner function, the exponent, n log x. Derivative with respect to x. N's a constant. We can bring that outside the differentiation. Derivative of log x is 1 over x. So we get n times 1 over x, or n over x. X to the n divided by x, that's x to the n minus 1. Lo and behold, the derivative of x to the n is n x to the n minus 1. We couldn't do this in the past because we didn't have this expression for x to the n in the past. We didn't have it until now. And we didn't know how to do this type of differentiation until we had covered the chain rule. So that's the reason this was delayed. The proof of this was delayed for, 5 sections. If x is less than 0, and the other hypotheses they gave us, if y equals x to the n, y prime, and x to the n minus 1, if all of these exist, then we have natural log of the absolute value of y is the same as a natural log of x to the n, y equals x to the n. The absolute value of x to the n is the same as the absolute value of x to the n, property of absolute values. Hey, we've got an exponent here inside a log function. We can bring it out as n natural log absolute value of x. Now, I mentioned in the past that if you'll differentiate log of the absolute value, we'll get the 1 over function. Here, that's the same as differentiating n natural log, absolute value of x. This is the example that's in the book. It's not in the notes. I leave it to you to deal with that. Differentiate log absolute value. You will get 1 over y dy dx. There's no absolute values involved. That's what that example demonstrates. Right-hand side, similarly, we've got an n. Differentiate log absolute value of x. You'll get 1 over x. Even if x is negative, you need the absolute values here. You'll get this out as a derivative. See example 3.8.3 part C from this section. Okay, so that differentiation, and the reason that's in there, so this can be done, that differentiation produces this. We're looking for dy dx, cross multiply, dy dx is, take the y to the other side, we get n times y times 1 over x. Y was x to the n, so we'll substitute in x to the n for y. We got x to the n over 1 over x. That's n x to the n minus 1, as claimed. So that establishes the whole thing, except in the case when x equals 0 and n is greater than or equal to 1. That's left as an exercise. So this is just a little special case that kind of slipped through the cracks of what we did. We did x greater than 0 in the first part. Here's x less than 0 in the second part. X equals 0 can't be that complicated to raise 0 to powers. But that's established as one of the exercises, one of the odd numbered exercises. Another example, a really flat example. Next, we'll differentiate y equals t to the 1 minus e power. All right, differentiate that with respect to t is the implication. Okay, well, you bring the exponent down and you subtract 1. Why did they wait till now to ask us something that elementary? Well, the reason is e is irrational, so 1 minus e is irrational. It's an exponential, it's a power of the variable with an irrational exponent. So we know now by what we just proved, the general power rule for derivatives, that to differentiate with respect to t to this power, I bring the exponent down and I subtract 1 from the exponent. The reason they felt the need to even bring this up, and I included it in the notes, is, it's because the exponent's irrational. And technically, until now, we didn't have a proof that this is how you differentiate with irrational exponents. But it's the same pattern. Bring the exponent down, subtract 1 from the exponent. It's simplified a little bit here. Nearing the end, little observation about this number e. We gave an approximation of the irrational number e in section 3.3 of approximately 2.71828182845 and some stuff. Where'd this come from? And even this is an approximation. It's an irrational number, so it has an infinite decimal expansion with no particular pattern, no repetition, I should say, no repetitions or no termination of the decimal expansions. That's what irrational numbers look like as decimals. So if you like memorizing digits of pi, there's just as many digits of e, so knock yourself out memorizing a million odd digits of e. But where's this come from? It comes from the following. So here's a formula. We actually stated something similar to this above. A formula that claims we can find the number e as the limit as x approaches 0 of 1 plus x it's 1 over x. So if we take values of x, well, error there, really close to 0. If we take values of x really close to 0, then we could plug those in, and that would be a way numerically to approximate e. For example, when x is 0.000001, we'd have 1 plus 0.000001. It's awfully close to 1. Yeah, but then it would get raised to the reciprocal of that 0.00001. It get raised to a really high power. And there's a balance between this being close to 1 and this being really big that yields the value e. We'll go through proof of that. We'll also look at a slight modification that allows us to express the exponential function as a limit as well. So we'll wrap it up with those two examples, let's establish this limit. All right, we're going to do it using the definition of derivative. Define f of x to be the log of x. Then you know f prime of x is 1 over x. So f prime of 1, plug in 1, you get 1 over 1, which is 1. So we're going to use the definition of derivative. That'll introduce a limit. That's a good thing because we want to talk about limits. So this one's a bit tricky. What is f prime of 1? Well, for any function differentiable at 1, it's the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. Replace the 1 with z's, or I'm sorry, with x's, and you get the original definition of derivative at point x. So we've got that definition of derivative with 1 plugged in for the x. There's the definition of the derivative of that function f at 1, f prime of 1. Let's take the h and replace it with an x. Right, this is written in terms of x's, so I'll first write it in terms of h's because you're familiar with this. Let's just throughout replace the 3 h's with an x. It's a dummy variable. Call it whatever I want. Haven't changed any of the numbers or anything. You know what the function f is. It said it's natural log of x. So f of 1 plus x is the natural log of 1 plus x. F of 1 is the natural log of 1. You may not know many values of the natural log function, but the natural log of 1 is 0 because e to the 0 equals 1. So that's a 0, and we're simply left with a log of 1 plus x divided by x, or 1 over x times the log of 1 plus x. How's it looking in comparison to this? Well, we got a 1 over x. It's not an exponent. There's a log function sitting there, though. And we got a 1 plus x. So we're in the neighborhood. There's a 1 plus x and a 1 over x, and where we're going and what we have. Hey, you've got a coefficient of a log function. You could take that coefficient and put it on this thing inside the log function as an exponent. Property of logarithms. Power rule of logarithms, I think it was. How do you feel about this? We got a blah, blah, 1 plus x to the 1 over x. Up here we've got blah, blah, 1 plus x to the 1 over x. So we're definitely getting warmer. This one has a log in the way, and it's in the wrong place. But wait, log function is a continuous function where it's defined on its domain. What do you know about continuous functions? I can take limits in and out of continuous functions. So I could take the limit inside that log function because that log function is a continuous function. It's the very definition of continuity. We define continuity in terms of limits. So take the limit inside the log function because you can. And now you've got the limit as x approaches 0 of 1 plus x, 1 over x. That's the right-hand side. Okay, there's a log function in the way and something's going on the left-hand side. But we're definitely getting warmer to the desired goal. All right, we said f prime of 1 is 1. It's stated previously. We had f prime of 1 was the log of that limit. So the log of that limit is itself 1. So we just replace the f prime of 1 with a 1 from the previous slide. We got a couple ways to move forward now. I could say the natural log of e is 1. We've got the natural log of something is 1. Well, that something must be e because a log function is 1 to 1. If you don't like that, I could exponentiate both sides. We could make this an exponent of e and make 1 an exponent of e. Then we'd have e to the natural log of this stuff, power. Well, the e in the natural log, inverse functions, would spit out what's inside the log function. On the right-hand side, we'd have e to the 1. So I can explain it in terms of 1 to 1ness of the log function, or we could exponentiate both sides, however you like. We'll end up down here, and that's exactly what we were trying to establish. The limit as x approaches 0 of 1 plus x to the 1 over x power equals e, which is a concise little way to express e as a limit. Here's something somewhat more general. It says a limit as n approaches infinity of 1 plus x over n to the n power equals e to the x, provided x is greater than 0. Provided x is greater than 0 because we're going to do some stuff with logarithms. All right, this one is also a bit tricky, but it's kind of similar to the previous one. It's exercise 102 from this section. So there's no lack of exercises in this 1,500-page book. All right, like we just did in that theorem, let's define f of x to be the log of x. I told you we're going to use logs. Here's where we need x to be greater than 0 so that this log function is actually defined. If f of x is a natural log of x, its derivative is 1 over x. And so we have, by the definition of derivative, the following. It's the same thing we just did, except in the theorem, we didn't have an x, we had a 1. So we had 1 equals f prime of 1, and we had f of 1 plus h minus f of 1 before. So it's the same technique, we're just doing something a little bit more general. So f prime of x, we know the derivative is 1 over x, and we know by the definition of derivative, it can be written as this limit. F is the log function, so we get the log of x plus h minus the log of x over h, because that's what the function is. Okay, now we're going to exponentiate both sides up front. So we're exponentiating 1 over x, that is we get e to the 1 over x, and we're exponentiating this stuff. So we get e to the limit as h approaches 0 of this quotient. There it is, written kind of on a single line to make it fit. So we've exponentiated both sides. If these sides are equal, e to this side equals e to that side. Exponential function's a function, so we plug the same thing in on both sides. In this equation to an exponential function, it produces something that's equal, but wait. Hey, exponential functions are continuous for all real numbers. So you can bring that limit as h approaches 0 outside of that exponential function. Limit came from inside the exponential function to outside the exponential function. When can you pass limits in and out of functions? When those functions are continuous. And the exponential function is big time continuous. So we can bring the limit outside. All right, why would you want to do that? Well, really, I'm trying to get rid of this exponential function. And I see an exponential function and a log function close to each other. Not close enough, so we still got some work to do. Hey, the log of x plus h minus the log of x, difference of logs is the same as the log of the quotient. So we can take this log of x plus h minus log x and write it as the log of x plus h divided by x. Property of logarithms. Log of a quotient over here is the difference of the logs over here. And I still got this divided by h thing lingering around. Hey, let's take that 1 over h and make it an exponent. You can't argue with the validity of that, and that's what's done in the next line. So the 1 over h, a coefficient of this log function, is made an exponent. So we've got exponents inside logs inside exponential functions, so it's pretty convoluted, but you can't argue with the validity of that. Why would I want to do that? Well, now I got this exponential function right next to its inverse, the natural log function. So when you exponentiate a natural log, you lose both of those, composition of inverse functions. This is the thing I've said, it's like they cancel, but it's not really cancellation, it's something else. But they're gone. And you're left with this stuff here. You're left with x plus h over x to the 1 over h power, x plus h over x to the 1 over h power. And we're still carrying the limit out front. Let's split this up. X goes into x one time, provided x is not 0. It isn't, it's positive, was a hypothesis. So we get 1 plus h over x to the 1 over h power. Here's what we got. We got e to the 1 over x equals the limit as h approaches 0, 1 plus h over x, 1 over h. Does that look like this? No. We want e to the x, not e to the 1 over x. We got an x over n at least. No, we get an h over x. That's no good either. So we need to do a little modifying. We'll do it on the next slide. But we got e to the 1 over x equals this limit. And this isn't what we're looking for exactly. We're getting there. So here's where we left off on the previous slide. Actually, to get to the final part about n approaching infinity, if e to the 1 over x equals this two-sided limit as h approaches 0, then e to the 1 over x equals the limit as h approaches 0 from the positive side. So I'm only taking half of the information down here. And I got my reasons. It's got something to do with n approaching positive infinity. So I'm throwing away the fact that when h approaches 0 from the negative side, we also get an equality. I'm not using that part. I'm just using this part. If the two-sided limit exists, then both one-sided limits exist. Okay, I'm using this one. Because I want to replace h with 1 over n. Right, we got a 1 over h in the exponent. Over here we got an n in the exponent where we're going. So let's swap those. Replace h with 1 over n. But h was approaching 0 from the positive direction. Well, if h approaches 0 from the positive direction, that's going to imply that n needs to approach infinity, positive infinity, and vice versa. So replacing h with 1 over n, noticing with that replacement, h goes to 0 from the positive side if and only if n approaches positive infinity. That's why I had to look at the one-sided limit deal. Then we can make the substitution, replacing h with 1 over n, or 1 over h with n, same thing. So the 1 over h becomes an n, the h becomes a 1 over n, and the limit as h approaches 0 from the positive side is replaced with the limit as n approaches positive infinity. So we've made those replacements to create this equation, which is closer to what we have up here. We've got a limit as n approaches infinity, right? 1 plus x over n, 1 plus 1 over nx, at least we got the n in the denominator, to the n power, to the n power. So the only thing left that's not quite the goal is we want the x in the numerator and we got it in the denominator. How about the other side of the equation? We want e to the x? Yeah, we got e to the 1 over x. Well, let's just replace x with 1 over x, because this was good down to this stage for any x greater than 0. Well, if it holds for x, and it holds for 1 over x, because if x is positive, so is 1 over x. So just substitute x with 1 over x. So replacing x with 1 over x, or 1 over x with x, same thing. E to the 1 over x becomes e to the x. The x in the denominator becomes an x in the numerator, and that's what we were looking for. So the last little trick just moves the x from the denominator to the numerator in both places. We can do that as long as we just replacing the x with something we know to be positive. If x is positive, 1 over x is positive. If x is positive, 2x is positive, and we can replace x with 2x for that matter. But this is where we were going, and that's why we made that substitution. There's e to the x. That exponential function written in terms of a limit. By the way, I don't think this is mentioned in the notes, but if we took x equal to 1, we'd have e to the 1, we'd have e equals the limit as n approaches infinity of 1 plus 1 over n to the n power. So here we could plug in a large value of n and get an approximation of e. What we had previously was a limit as x approaches 0, and you could plug in numbers close to 0 to get approximations of e. Here's where we could plug in big numbers to get approximations of e, replacing the x with a 1 to get e to the 1 power, e itself. And that's everything excellent, everything from section 3.8. This was on inverse functions and logarithms. So we've taken care of logarithms. What's left in the next section is inverse trig functions. And we know how to differentiate an inverse function in terms of the original function itself. It was that theorem, it was theorem 3.3, wasn't it? So we'll use that in the next section to deal with inverse trig functions, and then you're there. You know how to differentiate probably every function you'll ever encounter. Trig functions, log functions, exponential functions, inverse trig functions, all the algebraic functions. You know how to differentiate all of those once we do the inverse trig functions. There's no additional rules of differentiation to learn. You know everything there is to know about differentiation. I lie a little bit because there's actually an area of math called special functions out there somewhere. So there are some other kind of fundamental functions, but you're basically there. You know pretty much as there is to know about differentiation once we finish the next section. So I think it's Miller time. I will see you soon in section 3.9, and we'll do inverse trig functions. Have a nice day.